Before getting into the next lesson, try this warm-up. Draw a sketch of the function f of x equals x minus 3 squared. You might have to reach way back in your memory to see if you can remember how to do this, but try it. From grade 10 math, you might have remembered how to draw graphs of parabolas. This looks like the vertex form. So when I read the vertex form, the number in my brackets indicates where the vertex is. So this would show me that the x coordinate of my vertex is at 3. Since I have no number at the end, that means my y coordinate is 0. So there's my vertex. And the number at the start, it opens up. So my parabola opens up like a U shape. Okay, so I just wanted to get that back into your mind because it's probably been a while since you've accessed this information. But we look at the brackets, and that indicates to us where our vertex is for a parabola. And all that leads into our topic for this lesson, which is on multiplicity and sketching polynomials. So just like I got you to sketch a graph in the warm-up, we're going to start sketching graphs of polynomial functions. And before that, we're going to talk about this idea of multiplicity. Okay, so our whole goal is to be able to use your knowledge of properties of polynomials to predict and sketch the graph of a polynomial function, and then you're going to develop an approximate equation to model a graphed polynomial. So look at the graph to make an equation, look at the equation to make a graph. That's basically what we're going to be looking at in this lesson. I'm just going to walk you through some basic information, an overview, if you will, of different kinds of functions. We're going to look at linear, quadratic, cubic, and quartic functions. We're going to note some patterns, and then we're going to put it all together for this idea of multiplicity. So for a linear function, you can all imagine a graph. It looks like this, okay? The shape is called a line. No-brainer, right? Anyway, let's look at some information. How many x-intercepts are there in a linear function? Well, it will only ever cross the x-axis in one spot, so there's going to be one x-intercept. Now, what's the behavior at the x-intercept? Well, if I were to look right here and zoom in, it would look like this. That'll come in handy later. Behavior at ends. What do I mean by that? Well, the ends. Look over here and over here. I have arrows. If I read the graph left to right, though, I can see that the end on the left and the end on the right are going in opposite directions. So just keep all this information in the back of your mind. I'm going to move on to quadratic functions, and we're going to start to find some patterns. Okay, for quadratic functions, you could have a graph that looks like this, or like this, or like this, something like that. The shape is called a parabola. Now, the number of x-intercepts, well, I just drew it over here. If you have something like this, there are going to be no x-intercepts. If you have one like this, where the vertex is right on the x-axis, then that is one x-intercept. And if you have a parabola like this, it can cross the x-axis at 2 different points. So it can have up to 2 x-intercepts. Now the behavior at the x-intercepts. Well, if I zoom in here or here, it will cross the x-axis like a line, whereas here it will cross, for lack of a better term, like a parabola. So it'll look like these. And the behavior at ends. Well, for any of the cases that I drew, you're entering and exiting, going in the same direction. Now let's look at cubic functions. If I were to put a cubic function on a graph, you might get this kind of a shape. Okay? But you might end up with something like this, or this. So you can have no x-intercepts. You could have 1, you could have 2 like I've drawn here, you could have 3 like I've drawn here. So the number of x-intercepts is up to 3. The behavior at the x-intercepts, well, if you look at all of them, they all cross kind of like a line, except you could have this. So in the behavior at the ends, well, if you look at the end behavior, they're going in opposite directions. So maybe you're starting to see some patterns emerge. Let's keep going to the next kind of function, the quartic function. Quartic functions, you can have them look kind of like this. Something like that. I think you're getting kind of the pattern right now. With these types of functions, you can have up to 4 x-intercepts. At the x-intercept, the graph can behave kind of like a line or kind of like a parabola. And then the behavior at the ends, well, we can see they're going in the same direction. Okay, so let's just kind of catch up here. Linear, quadratic, cubic, quartic. This is a polynomial with degree 1. This is a polynomial with degree 2, polynomial with degree 3, polynomial with degree 4. So you can see the odd number degrees have a similar shape, just the higher the degree, the more twists there are in the middle. And the even number degrees have similar shapes on a graph. It's just there's more twists in the middle the higher the degree is. Okay, so if you have an odd numbered degree in your polynomial, the graph is going to have kind of a linear shape overall. And when you have an even numbered degree in your polynomial, the graph is going to look kind of like a parabola. And again, the number of twists in the middle just depends on what other numbers are in the equations. And this brings me to the idea of multiplicity. Multiplicity is a concept that relates the root of a function with the degree of the factor, the root, okay? So when we look at an equation in factored form, the factors are what we call the root of the function, or they tell us the root of the function. And so we can figure out, based on the exponent that's on the factor in the factored form, how that function is going to relate at its x-intercepts on the graph. So I'm going to show you a chart to kind of break this down for you. Now remember, all of this is just stepping stones to help us eventually be able to draw accurate sketches of the graphs of polynomial functions, okay? So in the factored form, let's say you had a factor that looked like this, x minus 2 with an exponent of 1. So if you don't see the exponent, it just means you have an exponent of 1. This is a first degree factor here. Now, if your factor says x minus 2, then that means your x-intercept is positive 2, 0 on the grid. Now the characteristic, what do I mean by that? Well, what does it look like at the x-intercept? So if you have a first degree, so if you have an exponent of 1 on your factor, that means on the graph, if you zoomed in at the x-intercept, your function is going to go straight through in opposite directions on either side of the x-intercept. Okay, just to speed things along here, if you have a second degree polynomial here, so if you have a factor x minus 2, but it has an exponent of 2 on it, in this example, the x-intercept is at the same point on the graph. Same with down here. For all of them, we're looking at the same x-intercept. It's the only difference between all these examples is that the exponent on that factor in your equation is different. And that's going to change how your graph behaves. Okay, so if you have an exponent of 2 on your factor at your x-intercept at 2, 0, your function's going to change direction at the x-intercept. Now, if you have an exponent of 3 on your factor in the equation, then at your x-intercept, you're going to come in from opposite directions, but you're going to kind of twist a little bit on the x-intercept. And then we start to repeat. So now we have x minus 2 as the factor with an exponent of 4. So when we look at the graph, our x-intercept's in the same spot. But because we have an even number degree, even number exponent, our graph is going to go in the same direction off of that x-intercept. It's going to change direction at the x-intercept. And lastly, let's say we had x minus 2 to the exponent 5. We're going to come in from opposite directions, and we're going to twist a little bit on the x-intercept. So it's kind of a turning point. Okay, so as you can see, when the exponent on your factor in the equation increases, the behavior of the function at that x-intercept changes. We can see it repeats. So when you have an exponent of 1, the function goes straight through, but when it's 2 or any even number, it's a full turning point. The function goes in opposite or in the same direction on and off. Whereas if you have an odd number exponent, your graph's just going to twist a little bit but still enter and exit from opposite directions. Okay, so we can use this to figure out what our graph is going to look like. Okay, so just to sum up, if you have an odd degree, you're going to enter and exit with opposite direction. And if you have an even degree, you're going to enter and exit with the same direction. For my first example, we're going to use all that I just talked about to sketch a graph of this crazy looking function. Okay, but fear not, it's already in factored form. So we have all of the factors. You just have to look at the exponents on those factors to figure out the behavior at those x-intercepts. So, first off, let's figure out where our x-intercepts are. Well, remember, the x-intercept happens on the x-axis when the value of y is 0. So really we're saying 0 equals this equation. Well, from previous lessons, you already know how to solve an equation that's equal to 0 in factored form. So x plus 4 is going to equal 0, in which case x equals minus 4. So I'm going to put that on the graph. That's one of my x-intercepts. So right there, x equals minus 4. There's an x-intercept. Now over here, x plus 1 is a factor. If x plus 1 equals 0, then x equals minus 1, which is right there. So there's another x-intercept. Over here, my factor is x minus 2. So if x minus 2 equals 0, then that means x equals positive 2. So there's another x-intercept when x is 2. And my last factor is x minus 4. So if x minus 4 equals 0, then x equals 4. So there I have another x-intercept. Okay, so if I have 4 factors with x in it, that means I'm going to have 4 x-intercepts on my graph. Okay, now let's look at the overall degree. Add up all the exponents on all the factors. Well, there's a 2, there's a 3. Don't forget the 1 on this one, and then a 2. So 2 plus 1 is 3, plus 3 is 6, plus 2 more, that's 8. So this has a degree of 8. And my lead coefficient is positive, so my overall shape is going to be more like a parabola. Now, as to how many twists are in the middle, that remains to be seen, but my overall shape is going to look like that parabola. Okay, now I'm going to get looking at how does the function behave at the x-intercepts themselves. So my first x-intercept belongs to this factor in my equation. It has an exponent of 2. So if you look at that chart that I went through before, it's going to behave kind of like a parabola at that x-intercept. My next one, x plus 1 with an exponent of 3. Well, that means there's going to be a little bit of a twist at that x-intercept, but it's going to go off in opposite directions. X minus 2, so at this x-intercept, the exponent is 1. It's going to go straight through from one side to the other, no twists. And my last one, x minus 4 with an exponent of 2, that means we're going to enter and exit from the same side. Okay, so I've kind of shown you what the behavior looks like at each x-intercept. Now I just have to put it all together. So my function's going to come in, turn again, go down and back up, straight through, down, twist, and back up. Enters and exits from the same direction. So overall, we've got the shape similar to a parabola. We've just got some twists in the middle based on what we saw here. The degree for each factor tells us the behavior at each x-intercept. Now, just a side note here, this is not an accurate graph. This is a sketch, okay? But the important thing that I'm looking for when I ask you for a sketch is that you have x-intercepts in the correct spots and that you have this, the overall shape is good and you've got the twists and turns in the right spots. Next, we can kind of use the same thinking to figure out what the equation is when you have a graph. Okay, so what we need to do is first figure out all the roots or the x-intercepts or the zeros, same thing. So we've got one here when x is minus 4. We've got another one here when x is 2. So this x-intercept corresponds to a factor of x plus 4 in my equation, and this x-intercept corresponds to a factor of x minus 2 in my equation. The other thing, at this x-intercept, the function goes straight through. There's no turns or anything on it, so I know my exponent is 1. At this x-intercept, the function turns. It enters and exits from the same direction. So I'm going to have an exponent of 2 on this factor. Now I have this coefficient of a. I don't know what that is, so right now I'm just leaving it as an a. Okay, so this is the start of my equation. F of x, so this function, I'm calling f of x, it's equal to some coefficient multiplied by, okay, these factors. These are the roots. X plus 4, x minus 2, and it's squared because of the behavior of the graph at that x-intercept. Okay, our next task is to figure out the value of this coefficient. And to do that, I need to know another point on the function. So if you look right here, that's a convenient point. It's right on the crosshairs. The coordinates are minus 2, comma, 5. So when x is minus 2, y is 5. So I can just sub those values into my equation. Remember, x is minus 2, so wherever I see an x, I replace it with a minus 2. And when x is minus 2, the function is equal to 5, so I replace the value of my function with 5. So now I have an equation with my unknown of a. Now I can solve. So brackets first, then the exponent, then the multiplication. Now I have to divide both sides to isolate for a, and I get my value of a. Okay, so a is 5 over 32. Now I can take that value and plug it into my original function. So I have f of x equals 5 over 32 times x plus 4 times x minus 2 squared. And that's the equation for this function. And this is my very last example for this lesson. We're going to do the same thing as the previous one. Determine an equation for this function. So notice the x-intercept here. There's a little bit of a turn in the function. It doesn't go straight through. Okay? This one, it goes straight through. This one comes on and off in the same direction. So I would actually like you to try coming up with an equation for this function on your own. So pause the video. If you need to look back at the previous example to help you, go for it. But I'd like you to pause the video and try this on your own and then check back in when you're done. Okay, so this x-intercept of -4 corresponds to a factor of x plus 4. Since there's a twist, but it still comes in and out in opposite directions, I'm going to say the exponent is 3. At this x-intercept, when x is -2, that corresponds to x plus 2 as a factor. The graph goes straight through, no twists, so the exponent would be 1, and this x-intercept is 3, which is x minus 3 as a factor. The function enters and exits the x-intercept on the same side, so that's an exponent of 2. I also found this point, 0, -8, that I could sub into my equation for x and y, and then I just did in the brackets, did the exponents, did the multiplication, divided both sides, and got my value for a. So I ended up with this as my equation for the function. Now, if you used a different point than I did, you should get about the same answer. If you rounded differently in the middle, you might be slightly off, but we should be approximately the same. All right, so we looked at taking an equation and making a graph. We also looked at a graph making an equation. So both those things you need to know how to do. And just remember, the x-intercepts correspond to the factors in your equation, and the exponents on the factors relate to how the function behaves, whether there's twists or turns or if it goes straight through. And if you get all those things down pat, you should be good. Now it's time to practice. So if you try the practice questions and you run into any difficulty, please let me know and I'll do my best to help.